Next on our journey towards an algorithm, we introduce a special kind of matrix called a Gauss transform. Here's our appended system again. And we're still going to reduce our appended system to an upper triangular form, but now we're going to use Gauss transforms. Recall that before we computed these multipliers, and I've gone ahead and filled these in this time. We used these to take an appended matrix and reduced that appended matrix or appended system to upper triangular form. And then we could do backward substitution. What we're going to do instead is think of these numbers as a matrix or an appended matrix. And what you learned in an exercise leading up to this video was that if you picked a matrix in a special way, then it has the exact same action as if you took a multiple of one row and subtracted or added it to another row. Okay? And in particular, the way you want to pick that matrix is to compute the multiplier, but then negate that multiplier. So we do that right here. And when you then multiply that times the appended matrix, you get exactly the same result as you did when you took multiples of the first row and added those to the other rows. And then we can do that again. We can compute our multiplier to be minus 16 divided by minus 10, but we need to take the negative of that. And when we then multiply that, we get the upper triangular system, or the upper triangular appended system that we wanted. And then we do our back substitution again, and we check our solution again. Now, this is still a systematic way for transforming the linear system into an upper triangular system. It's still the case that we want to do so because then an upper triangular system is easier to solve. We still represent the equations as appended matrices, and we still compute with the appended matrices. The only difference is that now we are converging towards an algorithm by casting the computation in terms of the application of a Gauss transform.